this work is to give you a new application for quantum simulation, which is using it to learn Hamiltonians for unknown systems. So this work I did with Chris Grenade and Chris Ferry, along with David Corn. And so, to begin, one of the big motivations behind this is to address what I view as one of the biggest problems facing the simulation community. So to begin with, let me talk about the two sort of broad paradigms that people often use to discuss simulation. There's the one which I'm always a big proponent of, which is a digital simulation, which of course uses a big series of gates, ideally fault tolerantly, in order to be able to emulate the dynamics of the system that you're interested in. And one of the really nice things about this is that if you know that each of these the gates in the network has some fidelity with the actual gate you want to implement, you can figure out what the maximum error is going to be in implementing the network. So you can come up with rigorous bounds on how far off your simulation is, which is awesome. But unfortunately, something that's less awesome is the fact that we can't do this for interesting problems. So, at least yet. So that's a downside, but maybe analog simulation provides an answer to this. And the idea, of course, with that is that what you want to do is you want to build a purpose-built system that doesn't have this gate network structure to it, that directly emulates the dynamics of another quantum system. A big drawback of this approach is the fact that there's no known way, at least to me, to be able to efficiently bound the error in the approximation between the simulator and the actual device. But a huge upside is the fact that these things actually exist. And you can build these devices with hundreds of qubit-ish, or two-level systems at the very least. I don't necessarily know how much coherence there is in those experiments, but you certainly can do hundreds of experiments in hundreds of qubits in ion trap experiments and the like. So as for open problems, one of the big questions is, well, we don't have error bounds for analog simulators. So how can we come up with protocols to certify them in order to say that the Hamiltonian we think the analog simulator is simulating actually is the real deal? And the next question is, can we use quantum simulation to infer models for unknown physical systems efficiently? This is a problem with the resolution. You'll excuse me for a second.
We now know how to do that. Yeah.
Oh. All right, whatever. I don't use that part of it, much of that anyways. So basically, one of the things that our work provides is a suite of techniques that can be used actually in some cases to address these issues and use quantum simulators in order to certify other quantum simulators. Also, this gives you another way of doing experiment and attacking physics. By using a full-fledged quantum simulator interactively with some unknown system that you'd like to learn things about, it gives you access to a host of experiments you wouldn't be able to do ordinarily, perhaps with the controls that you directly have. So these are some really neat things. So how do we go about using learning physical models for this? Well, first off, let's take a look at the learning problem that we want to deal with. Let's assume we have some Hamiltonian that we want to describe a physical system with. We don't know. And it's a function of this vector x over here. And these are the model parameters that describe this. So in this case, we can assume, say, a linear model, where we have all of these subterms in here that are just multiplied by this. So each of these would be the coefficients for it. So if you imagine this being like an Ising model, this could be like the interaction strength between nearby qubits, or it could be the on-site magnetic field. And basically, the goal for the whole learning problem is just to learn this vector x that best describes the system based on whatever experimental outcomes you've got in front of you. So the way that we go about doing this is by using Bayesian inference. And the idea behind Bayesian inference is to say, all right, well, let's say that you have some preconceived notion of how likely a particular model is for the system. Then you receive some data. how should you update your confidence that that hypothesis is true, given that that data is given? Bayes' theorem tells you exactly how you ought to do this. And the way, this part over here, don't pay attention to it. It's a normalizing factor. It's not interesting. The interesting bits are on the numerator. This over here is the prior probability, which represents your knowledge or your biases from it. This over here could be the result of decades of experimental insight into the system. Or it could just be some guess that you came up with 5 minutes before the experiment started. Ideally, it shouldn't matter too much if you do enough experiments, but choosing a bad prior can really, really slow down your experiment. This part over here is the likelihood function, which says, given that this hypothesis about the system were true, what's the probability that the data would emerge? And this over here is known as the posterior probability, which is the probability that the model is true, given that the data was observed. So this is really what we want to find with Bayesian inference. Now, there are some upsides and there are some downsides to this, which the upside is this gives you a really neat way to say how big of an impact an experiment should have on your beliefs about the system. But the downside is this probability is not going to be tractable for most quantum systems. It requires you to do a quantum simulation. And that's where ultimately quantum simulation, one of the ways quantum simulation comes in. It gives you a way of computing these probabilities. All right, so another problem that ends up coming up is I gave you a probability distribution. How many hypothetical models could you have for an Ising model? The answer is an uncountably infinite number. Any of those parameters could be anything. So how do I actually represent this in a computer so I can go about and learn this in a sensible amount of time? And the answer is, what you do is you instead of having a continuous distribution over model parameters, say for this Ising model here, what you do is you approximate a continuous distribution by a set of discrete points. And then these discrete points over here are then updated. And the likelihood of each of these discrete models is used as a proxy for your overall knowledge of the system. And there's a whole bunch of techniques that we use in order to make this approximation work that I don't have time to get into. But this is the core of it. We use a particle cloud in order to approximate our prior and posterior probabilities of, for these given model parameters. And so the way that the Bayesian updating works, just to be absolutely clear about this, is we start with some prior probability distribution, and we have these weights, these discrete particles that we use to approximate that are spaced out in such a way as to kind of best represent this. We perform an experiment, we collect a piece of data, and we use that rule in order to update. And as we continue and go on and on, what should happen is this probability distribution will become ideally sharply peaked about the true value. And then at that point, you can terminate. The other nice thing about this approach is that you could actually even directly read off what your uncertainty is, because it's the width of this peak up here. So it not only gives you the best estimate in terms of the mean of the posterior distribution, but it also gives you an estimate of your uncertainty, which is a really cool property. So now, how does the quantum Hamiltonian learning part come in? So for our experiments, we assume that we have two resources. We've got a trusted simulator and we have an untrusted simulator. So this trusted simulator, I'm just assuming for the moment, is some device that you've got a lot of experimental confidence in that it works. And you use this as sort of your ground truth in order to assess the untrusted system with respect to this. Simplest thing you can do is this experiment that we call QLE type experiment, for quantum likelihood estimation, where you basically perform an experiment on the untrusted system, and then you estimate what the likelihood of that event would be by using your quantum simulator or quantum computer in order to sample the outcomes from that exact same experiment and see how likely it is, thereby computing the likelihood function. The more sophisticated experiment is what we call an interactive quantum likelihood estimation experiment, where what you do is you evolve forward under the actual system Hamiltonian, and then what you do is you swap the state into your quantum simulator and evolve backwards in time, doing an echo experiment. And the thing that's really nice, if you have the ability to be able to do this, is that this will descramble a lot of the evolution you see in your quantum state, giving you extremely clear information about whether your hypothesis is correct or not. So to give you an idea of how this works, take the following example. This is an example for a Boson sample. So imagine you have this system and you'd like to learn something about its underlying dynamics. It's known for Boson samplers that actually computing the likelihood function is sharp P hard. So computing the likelihood function of this is pretty much not on the menu for large systems. But what you can do is you can take this device and you get this inverse over here. Then any input you throw in here, if this is perfect, will come out as output. So you can use this echo type experiment in order to test whether your hypothesis is correct, that this system over here is actually the true inverse of that system. So to give you an idea about what happens with this, imagine you're looking at more like a general Hamiltonian. So a random Hamiltonian, this was done for a random local Hamiltonian. What it'll do is it'll do something like this. You prepare any initial state, like here I took a definite state at 500. And then under evolution, under the random local Hamiltonian, the probability smears out after a short time and becomes nearly uniform. And once this happens, then you get virtually no information about what the system is doing because all of these likelihoods are just about the same for every outcome. So this is really bad for learning. But by doing this echo type experiment, you can descramble the scrambling step that happens at this output level and get back your initial information. This gives you a really decisive experiment about what your Hamiltonian is. So the next thing I should mention is how there's two parameters here for these sorts of experiments. One, you have to choose the model that you invert under. The second is you always get to pick your evolution time. You want to pick your evolution time to be short enough so that if you guess an incorrect model, it doesn't completely scramble and it doesn't cause you to lose all of your information. But you want it to be long enough in order to give you decisive information. So the happy medium that we end up finding is from this particle guess heuristic, which we do in order to sample points such that on average these two tendencies are kind of optimized. So when we use this guess heuristic, one of the things that we find is some pretty neat results. First thing is that if we just did the experiment directly and without using inversion, then we find that this the Bayes risk, which is essentially the expected amount of information that we get from the experiments, compared to the optimal, which is this dashed line down here. If you average it out, it's really far away from optimal. But if we apply inversion, then things improve. Because these dips up to the worst possible case become less and less frequent, whereas here, they're happening all the time. So you're much less likely to fall into an uninformative experiment if you use inversion. But if you use inversion with this guess heuristic, one of the things you'll notice is actually nearly exactly tracking the best you could possibly do information theoretically for this simple 1D system. So this guess heuristic, although non-rigorous, it tends to actually work very well. It's the saturated information theoretic lower bounds for simple systems. So to give you an idea of how the learning algorithm works, first thing we do is we draw our probability, our prior probability distribution and approximate that using a finite bunch of particles. And this probability distribution is stored on an ordinary computer. There's nothing quantum about this, right? It just represents your confidence that model X is true for the system. Then we perform an experiment using that particle guess heuristic that I mentioned and estimate the likelihood that the experimental data came back. Then we perform an update according to Bayes' rule. And if the uncertainty specified by the width of your posterior distribution is small enough, then you stop. Otherwise, you just keep collecting data until you get enough, and then you return your estimate of what the best model is. And this is efficient if every time you perform an experiment, you learn a constant fraction of a bit of the true model back. Also, if you require a polynomial number of particles to describe the prior or posterior distribution. Number two, actually, there's good reason to suspect that for all physical models, this one will hold. Also, you have to assume, in order for the inference algorithm to be stable, that you don't run into any really unlikely experiments, i.e. an experiment where the probability of that outcome was exponentially small. So that's the third caveat that we need. But if all three of these are satisfied, then you can actually efficiently learn the Hamiltonian that underlies the system that you're dealing with.
Do you know what how the number of cycles scales with the dimension of that vector x?
Okay, exactly. I'll get to that soon. This will actually depend on the model that you're dealing with and the set of experiments and the way you set it up. This actually really is a problem of more of experimental physics than of theory. But I'll show you some numerical examples of how it tends to work. So in order to get an idea for how well this ought to work in principle, we apply this to learning Ising models. And we focus on Ising models because of the fact that we've got tens of thousands of particles that we need to simulate. And so we need to do something that we can solve extremely quickly. Of course, if we had a quantum simulator to do this, there's no reason why we would need to restrict ourselves to such simple models. But since we have to do this in an ordinary computer, this is what we pick. We allow interactions between the qubits in the Ising model to either be on the line or the complete graph. Most of the data that I give will be for data from the complete graph. Right. So here's the first one. So first thing that we end up seeing from this is this quadratic loss is essentially like the square error. And we see that as the number of experiments end up increasing, the error ends up falling off exponentially. And one of the things that's really neat about Bayesian inference for these purposes is after only about 100 experiments, your error in the overall Hamiltonian for these 3 qubit cases is going to be with high probability about 10 to the minus 3 or 10 to the minus 6 if you look at the square error. So this is a small amount of information. Only 100 bits came back from this experiment. And already you know what the Hamiltonian is really well. And the key point, though, is that all of these are satisfying this assumption of learning a constant fraction of a bit per experiment. Yeah, Andre?
So that on IEEE float point number is 53 bits, right?
Right.
So in about that number, you get 2 float point numbers. And this is how much you need, right?
Yeah, you can extrapolate from these curves down and figure out at what point machine epsilon it won't be sufficient for these. We stopped well before machine epsilon was a problem, though. So now the question is, well, you looked at those plots, and for the many qubit case, Hal, do you have a question?
Oh, no, that's
okay. For the many qubit case, the case with 9 qubits, you notice that learning was a lot slower. So you might think, well, maybe actually there's an exponential barrier. Maybe learning ends up getting worse and worse and worse, which comes back to Mike's question. So what we did is we plotted this out, and we found that, not so surprisingly, the rate of learning does not depend explicitly on a dimension of the system. Instead, it depends on the number of variables that you need to learn. So we find that here, plotting this out, we end up seeing that there's good evidence. Unfortunately, we couldn't stretch the line graph case far enough to be really compelling. But there's good evidence that this is following a 1 over d relationship. So where d is the number of variables that you need to learn. So the point is that it doesn't seem for any of these experiments that we've looked at that the dimension of the physical system is relevant. And from the perspective of learning, it should be completely irrelevant because it doesn't ever fall in directly to the learning problem. To really nail this point, what we did, we also did another experiment where we considered the following case. We considered a 6 and 4 qubit problem, where all of the couplings were taken essentially to be uniformly at random between 0 and 100, plus 1% error in each of the couplings. So essentially, this is this begins as a 1-parameter model, and then what ends up happening is that the 4 and the 6 qubit cases are learning at equivalent rates because it's essentially just a 1-parameter problem there. At this point, the learning algorithm needs to know these small fluctuations in these coupling constants in order to keep making progress. And at that point, the two performances begin to diverge and follow exactly the same slopes that were predicted from the original learning problems for the uniform graph. So the point is that the thing that actually matters isn't the dimension at all. It really is just the number of effective parameters that you need to learn for the system. And that this Bayesian algorithm actually can adjust itself on the fly with no human intervention to learn at a rate that's appropriate. Now the question is, what about modeling errors? Anytime you specify a mathematical model for a physical system, you're wrong. Period, full stop. So there's always going to be couplings you don't consider. What happens then? So we did this. What we did is we said, okay, well, let's assume what we have is we give our simulator that's certifying the unknown system a linear graph. But we allow the real system actually to have interact on a complete graph with exponentially decaying couplings. Maybe dipolar would have been more reasonable, but we focused on exponential. The point is that at first, absolutely nothing happens. It continues learning just fine until, just like before, it needs to learn these couplings that aren't in its model, at which point it gets confused and it stops learning. But nothing catastrophic happens. And in fact, this plateauing is really interesting because it says that your model isn't good enough, that you need to throw something else in order to explain the data that's coming back. And this again happens for 8 qubits very quickly. Only 100 experiments are needed for that. Sure. So what about inexact likelihood calls? Because the likelihood is found by sampling from a quantum simulator. 10% error doesn't qualitatively change anything. Other error numbers essentially look exactly the same. How about noise robustness? This is really interesting. So what we did is we threw depolarizing noise at this learning problem. And we noticed that 5% noise doesn't change anything practically at all for this. And 50% noise has an effect, but doesn't really suppress it. Now this is partially because of the fact that we've got tens of thousands of particles in our particle cloud, so we're kind of averaging over all these instances of depolarizing noise. And because the depolarizing noise isn't colored, it doesn't catastrophically screw things up. It just slows the learning down slightly. What about realistic errors in the swap gates? Maybe that could torpedo our ideas. Well, turns out no. By including realistic models for superconducting qubits as well as quantum dots, we find that it still continues to learn at an exponential rate, even if we don't give it perfect swap gates. All right, well, what if we do non-commuting models? Maybe this was all particular to this. So we did some small examples with the transverse Ising model. We still see solid evidence of learning at an exponential rate. Okay, so this leaves one issue behind, which is this issue of a trusted simulator. Many might argue is an unrealistic assumption. And in some cases, yes, in some cases, no. If you wanted to use this for certifying an analog quantum simulator, then yeah, because you're building your trusted simulator will probably be at least as hard as building the analog quantum computer in the first place. So the question is, can we get around this and certify it with a much smaller device? And yes, you can. This is new work that we've just done. And the idea basically is that if you have a Hamiltonian that has local interactions, then what you can do is you can use a small trusted simulator that has a local observable here. And it turns out that what ends up happening under this physics is that for short evolutions, the effective size of this observable in here stays within the simulator that you can handle. So you actually, if you just stick to relatively short evolutions, can do this echo experiment without ever having this observable touch this part of the simulator that you can't simulate on your trusted device. So by doing this, you can actually simulate the dynamics of this observable using a much smaller system than the full thing. And so then, in order to learn what the couplings are, you simply scan over the larger system. Somewhat like this, learning along the way using Bayesian inference. To give you an idea about this, we applied this to a 50-qubit example. This has 1,225 parameters in it, so this is a big learning problem. We find after doing 500 experiments per phase of the scan that we take a distribution that has high probability of errors for particular couplings, essentially kill that after doing these samples and make almost all the errors 10 to the minus 5 or smaller. So actually, Andre, I'm going to have to finish up if I could take your question in Q&A. So to conclude, basically what I really want to get across is that quantum simulators and quantum computers really, in principle, are actually more than computational devices. If you can network them in with experimental systems or other devices that you want to learn something about, then what you can do is you can do some really interesting echo experiments that allow you to directly compare and contrast different quantum models. And this allows you to infer Hamiltonians for systems that you may not have been able to infer a Hamiltonian for. And the methods that we've proposed are stable, robust, and often will learn at an exponential rate. And looking forward, one of the key things that's really interesting about this is it opens up the possibility for doing quantum bootstrapping, wherein you follow the idea that I put forward on the previous slide to build a small quantum computer that you use to control and characterize a slightly larger one, which then you use to control and characterize a slightly larger one after that, and keep on snowballing up until you get to a really large quantum system. So the key point is that there's a lot of really interesting things that come out of trying to use a quantum computer to learn physics. Thank you very much.
Any questions? So is there some topological theory that guarantees that you can patch together the global state out of local scans?
Well, yeah, actually, well, one of the things is that there's the principle, the axiom of local tomography that allows you to do this. You can always reconstruct the state via local measurements in principle, but that's not really what I'm talking about. There is no global theorem saying explicitly you can do this, but you can explicitly do this if you have the assumption of local couplings. If you have couplings that cross the simulator, like, let me go back here. Like, say you have a coupling between a qubit that's here and a coupling between that qubit that is totally that's non-negligible. Then that isn't going to show up at all in any of your simulations, and that can corrupt things. But if you have only local communications, like this and that site will talk to each other, then this will suffice.
Any questions? The dimensions of these spaces are the dimensions of X, not of the system?
These are the dimensions of the system.
Okay.
So the dimension of X could be entirely unrelated. It could be a one parameter model that you're trying to learn for a 100 qubit device.
So the examples you show are basically the IC model did the calculation, and then if you have, for example, quantum IC model, basically you have terms that basically don't commute with each other. How is it going to affect the result? And
Sure.
also near the quantum critical points is how is this?
Well, as far as quantum critical points, these experiments don't necessarily reflect that, because quantum critical points are most interesting from the perspective of the ground state. And here we're not doing measurements that directly have anything to do with the ground state. So I expect this to be kind of blind to the quantum criticality. But the thing is that with non-commuting models, things become a little more interesting, because of the fact that if you've got a non-commuting model and you want to extract information out of this, then your choices of the measurement operator become really important. So you really have to start sitting down and thinking about how you best want to extract information from the system. For cases of commuting models, you can pick out easily what the best measurement operator is. But otherwise, you need to be a little bit more careful. But the ideas still work.
All right, we should move on to the next stand paper. Okay, so the next speaker is Lucas Lamata, who will discuss digital quantum simulation of spin systems and superconducting circuits.
Okay. First of all, I would like to thank the organizers for the invitation to present these results here. I'm Lucas Lamata, and I work at the University of the Basque Country in Bilbao, in the north part of Spain, and I will talk about digital quantum simulations of space systems in superconducting circuits. So probably you saw this slide also in Laura Garcia Alvarez talk this morning. So this is an overview of our group in Bilbao. It's led by Enrique Solano, and I have a tenure position there. And we are 15 people, and we perform research on quantum optics, on quantum information, superconducting circuits, condensed matter, and quantum mathematics, and receive money from a series of regional, national, and European sources. This is the outline of the talk. I will first put a slide on the topic of quantum simulations to see not only the typical aim that people have of outperforming classical computers, but also the interest that we have related to establishing analogies between unrelated fields that we believe is also very interesting. Although, of course, we also have the ultimate goal of outperforming classical computers in mind. Then I will enter into the two topics of this talk. First of all, I will speak about spin models implemented with digital quantum simulators in superconducting circuits. And in the second part, I will talk about the digital quantum simulation of the quantum gravity and quantum decay models in superconducting circuits. So, as I mentioned, many people have in mind the possibility to outperform classical computers with quantum simulation. But I would like to point out that, for example, when Dave Wineland and Niels was doing his experiments with a single trapped ion on the James Cummings model implemented with a single trapped ion. He was performing possibly one of the first quantum simulations of the interaction of a single atom with a photon inside a cavity, the cavity QED experiment, simulated with the motional degree of freedom of the ion as the simulation of the photon and the internal levels of the internal levels of the atom. So that was a very neat experiment, and we think that establishing this kind of analogy, for example, in that case, this gave rise to all the implementation of quantum gates in trapped ions and the experimental quantum computing. So Enrique will also speak tomorrow about one line that we pursue in below that I will not discuss here, but we believe is very interesting, implementing phenomena that go beyond physics and physical behaviors or even symmetry transformations or this kind of phenomena that can also be encoded in a quantum simulator. But of course we are interested also in implementing fermionic existence, spin models, and all these things that are interesting for outperforming classical computers. So in the role we work with different kinds of, we are theoreticians, but we work in close collaboration with experimental loops, both in trapped ions and in superconducting circuits. And we work with superconducting circuits mainly because we believe it's one of the most promising quantum platforms. It's highly controllable. We saw the talk by Rami Barnes this morning. You can implement very efficient 2-qubit gates. In John Martinez' loop, this goes beyond 99% fidelity. That is already comparable to trapped ion, but even for more than 2 qubits is even better. So this is a very neat quantum platform, and is perhaps the one in which the developments are being produced faster, because in the last decade or so, this is the platform that possibly has advanced more. And I would like to highlight some recent results like the teleportation in ETH Zurich by Andreas van Rooij, feed-forward techniques in Delft University of Technology, or here in California, in Santa Barbara, the high coherence qubits and gates. So let me now enter into the first part of my talk. I will review this paper that we produced in Bilbao in collaboration with the group of Andreas Valra at ETH in Zurich. And this is a theoretical proposal about quantum simulation, digital quantum simulation of spin systems in superconducting circuits. And the people that were doing most of the calculations are Uchi Laseras and Antonio Mechacapu. And there's currently an experiment ongoing in Valra's group at ETH, who have already done this for 2 qubits, and they are aiming now to more complicated scenarios. So for those of you who are not familiar with CQED, you can have typically this kind of Hamiltonian, in which you typically have a set of qubits that are made of superconducting islands with Josephson junctions and so on. And you have a bosonic degree of freedom, that is a microwave strip-line resonator, and you have the bosonic free part of the resonator, the charging energy of the qubit, the Josephson energy due to the nonlinear element of the Josephson junction. And then you have also the coupling of the charge to the motion, to the photonic and microwave photonic degree of freedom. And then it turns out that by having this kind of interaction, you can, for example, couple 2 qubits to a resonator, and you get, if you eliminate that with quantum optical techniques, you adiabatically eliminate the resonator, and you get the SY Hamiltonian that I saw here. So this is the exchange interaction in which you excite one qubit and you de-excite the other one, and so on. This is just the XX plus YY in terms of Pauli matrices. And this is the natural interaction that appears in superconducting circuits when you couple qubits to the resonator. But of course, this is a very limited spin model, because one will desire to perform an arbitrary quantum simulation of spin models that involves any possible spin Hamiltonian. That will be far more interesting. And then it turns out that the Heisenberg model does not appear from fresh principles in CQED, and we want to analyze the possibility of implementing Heisenberg or an arbitrary spin Hamiltonian by using digital techniques. And the composing in terms of the available interaction that appears in superconducting circuits, that is the exchange interaction. So this is basically the kind of approach we follow. Total methods are already mentioned here. So we have a target spin Hamiltonian, like for example, the Heisenberg Hamiltonian, for example, that this consists of X, X, Y, Y, and Z interactions. Here I wrote the homogeneous case, but we could also think about inhomogeneous case. And this is some either in a linear chain or in 2 dimensions. It could be a sum over nearest neighbors or whatever. Then one will expand this Hamiltonian. The evolution operator is expanded in a set of gates that can be efficiently implementable. You implement them in a short time scale, and you repeat this. This is a single thought step, and you repeat this L times, and then you have an error that decreases as 1 over L. Depends on the commutators of the different terms and higher order terms. And what we do is each of these gates we will decompose in terms of 2 qubit gates, the exchange gate, and single qubit gates. Because it's the technology that is available, for example, in Barra's group in Turing, and we work in close collaboration with them in relation to this experiment. So, let me now explain briefly the way to implement the Heisenberg model with this kind of interaction. So this is the available interaction. So for example, suppose that you rotate the XY model with just a rotation upon the x-axis, you get XX plus CC interaction. And if you rotate with respect to the y-axis, you get YY plus CC. Notice that if you have these 3 terms here, you just recover the Heisenberg Hamiltonian. And then you can just combine evolutions with different times or different couplings in each of the gates in order to have arbitrary inhomogeneous Heisenberg models. So when one applies Trotter methods, one implement each of these terms in a sequential way, and for 2 qubits, one just recovers the Heisenberg Hamiltonian without digital error. For more than 2 qubits, one should apply one step. So this is basically the sequence of gates that we envision here. We have the SY 2 qubit gates, single qubit gates, again SY, single qubit gates, SY, and single qubit gates. This is a single Trotter step that allows to obtain a non-trivial spin interaction like the Heisenberg model with the available interactions that are the SY interaction. So Andreas Ballard performed already the experiment with 2 spins. Of course, one will want to go to hundreds of spins or so. With digital techniques, so far one cannot go much beyond 2 or 3 spins, or 5, not much more so far. But we believe these are times in which in superconducting circuits, pioneering experiments and proposals are appearing, and then of course this will progress because this technology goes fast. And I hope that in the near future this can be extended to many spins. But for the moment, for 2 spins, there will be no Trotter error, and for you need just a single Trotter step. For 3 or more spins, you need to repeat this n times. So this will be the sequence of a single Trotter step for 3 spins, combining the 2-body exchange gates and single qubit gates. So this will be a single Trotter step with evolution of T over N, and you repeat this n times. Then another model one could think about is the antiferromagnetic interaction that is interesting. This has been performed in trapped ions in Chris Monroe group by Kim and co-workers a couple of years ago, and there they did an experiment with 3 ions in a kind of triangular lattice. And if you have a triangular lattice with antiferromagnetic interactions, then you have an interesting phenomenon that is called frustration, in which you cannot minimize all the bonds at the same time. And this is interesting because the ground state is highly complex, it's an entangled state, and you cannot solve this efficiently with classical computers. For some spin Hamiltonians, you have efficient classical algorithms because you can apply quantum Monte Carlo for computing static properties. But in general, if you have frustration or you have disorder or things like that, then you cannot apply this quantum Monte Carlo anymore because these are systems that are affected by the same problem, like fermions, for example, and then you cannot solve them efficiently classically. So we were interested in devising an algorithm for implementing the antiferromagnetic interaction in the circuit, and this is the following. So this is the Bayesian Hamiltonian. People already told about this in this conference. So in order to get this Hamiltonian, one could use a direct coupling between the qubits. In the Martinez group, they do this to get the sigma cell or the control cell, combining with 2 of them with local gates. This can be done that way. But another possibility is to combine the exchange gate with single qubit gates in this way. So you rotate one of the 2 qubits along the x basis, and then you get xx minus yy. Introduce a minus sign here, and then you can add the original exchange gate plus the rotated exchange gate, and you cancel the YY term, and you get that way the easy. It's interesting to realize that it's simpler to implement the exchange gate than the easy gate in cities, and you use other kinds of techniques like the direct coupling. But in this case, this does not imply throat error because the different tests commute, so you can just apply a single throat step and get very good fidelities. Of course, a more interesting model, and that is the one that is inefficient classically, is if you add a local magnetic field that can scan the different phases, different quantum phases that appear in the system. And I included here this term, so this will be a single throat step. In case you include these local interactions, local rotations, then you have to apply these gates that implement this part, the easing part, and then you add this at the end with local gates. And given that these gates do not commute with this, then you have to repeat the protocol n times to get full fidelities. This is the sequence of the easing part for a single throat step. As you see, the complexity is increasing, but Andreas Barrad is currently developing and experimenting with 2-3 qubits, something like that, as a proof of principle analysis of this kind of platform. So we perform also some numerical simulations of the digital error, also related to the accumulator gate error, because there's a trade-off. Of course, in digital quantum simulators, you have a digital error coming from the fact that the different tests in the Hamiltonian do not commute, and you are implementing them in separate unitary evolutions. But then, the more gates you apply, the smaller the digital error. But then, if you apply many gates, you will have a larger gate error, because you apply many gates, each of them with a finite error, because the gates are always imperfect. And then there's a trade-off. And we analyze this here, for example, this is the digital error for these two are for the Heisenberg and these two for the transverse antiferromagnetic easing. This is for 3 digital steps, and this is for 5 digital steps. This is for 2 digital steps, and this is for 3 digital steps. And this is the accumulator gate error that we consider for a certain amount of single antibody gate error. And as you can see, there's a region at the beginning in which the accumulator gate error is larger than the digital errors, but the digital errors grow with time because the term in the Trotter formula has a time dependence and it grows quadratically with time, the second order term. So in the end, you will have that the digital errors will overcome the accumulator gate error. So there's a trade-off of the number of gates you should apply in relation to the fidelity you have per gate and the digital errors that you have in the protocol. Then, in order to make a realistic proposal of this kind of models, we perform numerical simulations, including the full superconducting qubit Hamiltonian, including the third level of the transmode, because, as you may know, the transmode qubit is a qubit that is highly harmonic. It has the third level almost on resonance with the first 2 levels, and this means that this is good in order to have long coherence times, because then it's not sensitive to charge noise. But on the other hand, it turns out that due to strong drivings and on the first 2 levels, you could also have the third level and have leakage. So it's interesting to include the third level in the simulations for a certain anomalicity parameter and to check whether it plays a role or not, whether it is controlled the coherence of the 2 first levels that compose the qubit. So we consider the free part of the spins, the free part of the electromagnetic microwave field, and then the coupling between the 2. And we consider a master equation, a linear equation, in which we include the damping of the cavity, spontaneous emission, and deflation with realistic parameters in current experiments, for example, in Qubit or something. And this is, for example, the kind of results we obtain. So the fidelity can be above 0.8 for a long time, and in many cases almost larger than 90%, 90-something%, 99%. But then you have also this is the exact evolution with the Heisenberg model, and this is the simulated model. Of course, here we have a certain oscillations of the fidelity, but it can be about 90% as far as you do the tuning large enough. Of course, there's a trade-off here because if you put the tuning very large, then the dynamics is low, and then the coherence coming from spontaneous emission and the phasing could play a role. But on the other hand, if you do the tuning very small, then you have a higher order of perturbative pairs that will influence your system if you have strong clock. This is the people involved in the experiment in Turing. They submitted abstract to the mass meeting. They presented this in the mass meeting. And they have performed so far the Heisenberg experiment for 2 qubits with fidelities larger than 84%, fidelities that are even slightly larger than the one we predicted in our simulation, the one of 77%. And we think well, they have even better single integrated fidelities as we were considering in our simulation. And I would like now to enter into the second part of my talk, that is the digital quantum radiant decay models implemented with superconducting circuits. And this is a collaboration we have performed in Bilbao together with a group of Leo Di Carlo in the University of Technology in the Netherlands, who is also performing ongoing efforts in order to implement this proposal in his lab. So, to motivate the quantum simulation of the quantum radiant decay models, I would like to point out that this is perhaps the most fundamental light-matter interaction between, for example, a single atom and a photon inside a cavity. Of course, I would like to emphasize that this is the quantum Rabi model, not the Rabi model, because the Rabi model was developed in the 30s by Rabi for magnetic resonance, interaction of classical radiation field with atomic systems. But in this case, we are concerned with the exchange of single photons or a certain number of photons with a Thule resistance. In our case, it's really a quantum regime for the radiation field, so we call it quantum Rabi model. I think it's the correct thing. And this is basically the Hamiltonian one has the free part for the electromagnetic field, the free part for the spin, and then we have the coupling between the spin and the electromagnetic field. This kind of Hamiltonian appears in the dipolar approximation in lots of systems. For example, in trapped ions, the coupling of the two-layer system with the violation of the degree of freedom, or the superconducting circuit, the coupling of the qubit, the transform qubits with the stable resonator. But typically, what happens is that the coupling, this coupling here, is small as compared to these two frequencies, and then you can just perform the so-called rotating wave approximation and obtain the well-known James Cummings model that has a U1 symmetry, can dissolve exactly, and so on. The right model was believed to be non-integrable, but indeed Daniel Wright, a German physicist, showed that it's indeed integral, and he obtained an analytical solution just a couple of years ago. But we would like to really be able to implement this model in all parameter regimes in a quantum experiment. This has not been done so far. And a most interesting thing that I would like to emphasize is the extension of this model to many qubits. The so-called decay model, because there, for a certain number of qubits, this model is not analytically solvable, and for a certain number of qubits and a certain number of bosonic excitations, one never can be able to solve it with a classical computer. And for the decay model for, say, 20 qubits, 30 qubits with a certain number of bosonic excitations, one has interesting behavior on this matter, like super radiance, exotic quantum phase transitions, and so on. So we believe the approach we have here is very interesting to really reach this kind of, to begin with a quantum Rabi model as a toy experiment to begin with, and then to extend this to a decay model and so on, more complicated issues. So well, in atomic systems you have that the coupling in relation to the mode frequency is of 10 to the minus 6. When in superconducting circuits, this can reach the ultra strong coupling regime of 1/10 or 1.2, 0.12. So this is already a regime in which the rotating wave approximation begins to fail. And then there are other regimes, this strong coupling regime was developed in Bilbao, in which the coupling is larger than the mode frequency. But this has never been achieved in the experiment. So it will be very interesting to really solve this model for all parameter regimes in a quantum experiment. So it's very difficult to have a quantum platform and really reach this level or all the regimes of the ultra strong coupling regime. So a possible way to address this problem is to do a quantum simulation. So the main point here is that we have the James Cummings model. This is the model that we have initially in our platform. And then we decompose the or Rabi Hamiltonian in terms of James Cummings and anti-James Cummings models. The anti-James Cummings is like the James Cummings model with the excitation of the spin instead of the excitation. And it turns out that in superconducting circuits we can create anti-James Cummings interaction via local rotation with a sigma spinning matrix. And then we get the anti-James Cummings. And via digital decomposition we can retrieve the Rabi Hamiltonian in arbitrary parameter regimes. In the deep stone coupling or stone coupling arbitrary for all possible parameter regimes. And this is, for example, the sequence of frequencies that one has to apply to the qubits to achieve this problem. So we perform some analysis of the parameters for the stone coupling of the stone coupling regimes. The frequencies that we need for the qubits are achievable in superconducting circuits. And then we did some numerical simulations with master equation. This is a single instance of an experiment with the 15 digital steps with the realistic parameters for the regime of this coupling, where the coupling is equal to the frequency of the mode. And you can see here that this is the simulated point, this is the exact simulation, and this is with the superconducting circuit device. You can see here that it has collapses of the spin population on the wires, and the photons can go much above 1 up to 4. And then you simulate this point here. So this is the point we want to simulate, and after all the evolution of the simulator, after all the data steps, we retrieve the simulated point and we can make a new theory. This is including master equation with damping for the resolution dissipation. And then we did also simulations of the digital errors appearing in this kind of platform. You can see here this is the evolution, the survival probability of the initial state with respect to the exactly evolved state. You can see that the dynamics is non-trivial. It goes from 1 to 0.7 here, or from 1 to almost 0. So it's a real evolution that takes place inside this window of time. And then you can realize that the fidelities that one can get with the digital protocol are very high. So they're much above 90%. And this is for the ultra-strong coupling, this is for the deep strong coupling. So then one could extend this to a qubits, to a decay model, and this is becoming really interesting because with this model one can explore exotic phases of matter, superradiance, and things that one cannot solve analytically or numerically with largest classical computers. And for this we need only to add more qubits, add more copies of the qubits to the resonator, and we combine the Davis Cummings and these are the James Cummings but acting upon all qubits, and we combine this with global single qubit flips. And I would like to point out that a very important thing here is that the resources that we need are constant with them. Do not grow with the number of qubits. This was shown this morning also in the single execution space protocol is similar to that. The resources do not grow with n because the Davis Cummings can be done all at once upon all the qubits, and the interactions, the global single qubit flips can be done also at the same time upon all the qubits. This will allow one to close superradiance and one-way transitions and exotic phases that will be interesting also for learning novel things and performing classical computers. Then another point I would like to highlight because we think is neat is that the Rabi model, one has zero mode frequency, just collapses to a 1 + 1 Dirac equation. Probably you know that I proposed in 2007 together with Enrique and co-workers the quantum simulation of the Dirac equation in a single trap diagram that was later on done in Innsbruck, in Daimler-Blatt's experiment. But with this approach, one could already simulate the Dirac equation in superconducting circuits using these digital techniques. And we have this kind of acronym that we like to relate the quantum Rabi model with relativistic quantum mechanics. They are very, very much related, and we think that's interesting. So this is the Dirac Hamiltonian. You can see that this is like the spin part in the Rabi model, and this is the coupling of the qubit to the boson. You can see this as sigma x a plus a down. And this is as the Rabi Hamiltonian without mode frequency. The mode frequency is 0. So let me just conclude. In this second part, I have shown you a digital approach to simulate the quantum quantum gradient decay models in all parameter regimes. This one will allow one to simulate super radiance and non-analytical regimes and regimes that cannot be achieved numerically with classical devices. This can also be connected to relativistic quantum mechanics and another research line we are pursuing in the device, for example, as Laura Garcia shown this morning, is the quantum simulation of quantum theories in superconducting circuits. With this, I would like to thank you for your attention.
Have any questions?
Talk about basically transmitted and also use basically state 0, 1, 2, 6. So, so there are also other higher states. In this case, you actually have the decay problem in your case errors.
Yeah. In the case of the decay unraveling models, one could also include a third level, but notice that we won't have this problem because in this case the number of gates that one requires is small, and we are always in the weak coupling regime. Because the point is that we can reach all parameter regimes of the radiant decay models, the quantum radiant decay models, but in a quantum simulation. So indeed, the James Cummings model that we consider is in the weak coupling regime. So we make sure that we never excite the third level. We will keep only weak couplings. But the effective model that appears is a strong coupling regime of this strong coupling regime. It's a quantum simulation.
Thank you, Lucas. Yeah. Okay, so for the next talk in this session before coffee break, by Pedram, Roushan, an observation of topological transitions and interacting superconducting circuits.
Something so. Yeah.
So yeah, I'm Pedram Boson from UC Santa Barbara, and I'm a postdoc with the John Martinez group. And there is a small group of us in the John Martinez team, which we are working on the quantum simulation. But as Rami mentioned too, this really should be taken as a work of all of us who are working on different aspects of the material and all other questions like readout, coherence, and whatnot. This particular work is done in collaboration with Michael Qubits and Anatoly Polkovnikov from Boston University, and in various places during the experiments and design, we really benefited from Mike Skiller's help and collaboration. Thanks to Rami, he really put a good introduction to superconducting qubits. I don't need to say that again. So I just say a bit about quantum simulation and the challenges that we see as experimentalists. Then I go and explain the work of Anatoly Polkovnikov, which we implemented in this work. And then I walk you through something which we all probably familiar and construct a simple phase diagram, topological phase diagram. Hopefully all the terms become clear soon. And then at the end, we take it to the limit that is not as intuitive as the single qubit limit that we did the experiments. And this led to 3 works which are all under review and all on archive. What is the challenge of quantum simulation? You know, there are many platforms, and I would say with analog quantum simulation, probably no platform is going to win over the others. All of them have many good aspects, and they have their own challenges. But as we start touching them with our platform, we realize the challenges, at least the way we see it, is really in controllability, one of the major challenges. And in fact, it's related to coherence and such. So if you really want to have a full-fledged quantum simulator, you really have to be careful that you don't lose controllability as you scale the system larger. If you do that, I guess you get back to any good old experiments that we have been doing in many, many years. And it's not really different. That the vision that Richard Feynman did, it was just to have full control over the system, not to lose it. But it's a different challenge. It's a difficult challenge because it's very easy to isolate the qubits to get the good coherence and how you want to control them, which demands connecting to them, which that destroy your coherence. So it's a big challenge. And just to be concrete about it, if you have two qubits and you think about them, you know, two spin one-half systems, if you really want to control the interaction, the Hamiltonian of this system, it takes 7 knobs. And you know, you say, oh, is it linear or n squared or whatever? I don't want to even know, but that's what I see is even for 2 qubits is a big challenge. And this would be something we show how we kind of did that, well, for 2 qubits, like for now. But you know, the numbers are not that easy. You know, 7 knobs just to control very simple Hamiltonian, which you can do with pen and paper easily. So this is at least in my mind is a really major challenge. So okay, so what do we want to do? We want to study topological phases and construct topological phase diagrams. Okay, what are they? So before discoveries of integer quantum Hall or fractional quantum Hall, the Landau paradigm of local symmetry breaking was the only phase transition that we were familiar with. You know, you look at what local symmetry is, a system breaks, and that defines its phase. But in 1980s, we learned that besides that, there are phases that all, when you look locally, they all look alike, but the global properties are very different from each other. And that led to the definition of topological phases, which we are talking about the global property. So this global property brought some challenge with itself. How are you going to measure some global property? So mainly measurements are limited to like an indirect measurements, like you measure some global thing like a resistance, and from the behavior of the global measurements such as resistance, you infer some topological properties of the system. You see plateaus and you say, oh, probably I have edge states or so. But so it can be, the challenges can be studied them directly, and that's what the idea of Polkovnikov and company is about. So, but we like topological phases because they are robust. And in fact, for instance, for integer quantum Hall effect, we understand them in a sense that when you're doing a measurement of integer quantum Hall effect, you're really integrating over the local curvature. And the classical, the old-known theorem tells you that the integral of local curvature over a closed space is really insensitive to shape of the object. It just counts the number of holes in the object. So easily, that insensitivity brings robustness, and that's why we have these plateaus. So, and each of them represent a phase which are characterized by, for instance, topological invariant. In this case, they are known as the Chern numbers. So the question comes down to how do we measure Chern numbers, essentially. So the definition of Chern number is the integral of the Berry curvature over a closed shape like this one. So, okay, we need to measure the Berry curvature over this. Well, okay, I confine myself to 3D manifolds because we can work out nice analogies, as you can see, as I will tell you soon. But of course, it's not limited, anything limited to a 3D parameter space. So to measure local curvature, you can, go and, for instance, this point in the parameter space, you can go and measure the state of the system for that point, and you can do a dense measurement for each point and put them together, do the differentiation, and then measure the local curvature. But the Polkovnikov and company's idea was, well, alternatively, you can get a quantum system and move it in this parameter space and see how much the measurement is different from the one that was in the adiabatic limit, the true ground state of the system. And this deflection is telling you about the local curvature. The concept is very familiar to all of us. Then there is a curvature in the space, a straight motion would be deflected. And this deflection is proportional to the local curvature. For instance, we know from Lorentz force that if there's a magnetic field curve some region in the real space, then the particle, a charged particle, would be deflected. And that deflection is telling you about the local curvature, the local magnetic field. And essentially the relation of Polkovnikov is the same, although there's much more into it. It's not, they just put operation thing and just get into here. There's more into it. You have to do it with proper speed and whatnot. But it's interesting when you measure the churn eventually. It's very, again, the analogy with magnetic fields go further, that the measurement of the churn is very much similar to measurement of the Gauss's law for magnetic field. In a real space, if you have a magnetic monopoles integrating over the surface, measuring magnetic field over a surface, will tell you about the existence of magnetic monopole. And the churn number, it just happens in parameter space, and it tells you about the singularities of the Hamiltonian. And so Berry curvature in parameter space is like magnetic field in real space. So the analogy helps you guys to figure out what this churn is all about. It's essentially something very similar to Gauss's law. So with this in mind, let's see how we can implement their ideas, which require some dynamics. So let's start with a system, which we know rather well what the churn number of the system is. Let's consider a spin 1/2 system in a magnetic field. And from our quantum mechanics textbook, we know that the Hamiltonian of the system is this, and then the churn number of the system is 1 if you consider parameter space manifolds that are enclosing the origin of in the parameter space. So we need to move over this surface in parameter space. How do you construct that in the lab? Is, well, you get microwave lines, microwave drive with a sine profile and a detuning HZ with a cosine profile, and then you terminate them and you measure the state of the qubit as you go along. And because of the symmetry, you don't need to go any other meridian except this one I show, and at the end you multiply by that. So this is on the Bloch sphere. This is the state of the qubit during this ramp. So you're starting from here at this point in the parameter space. You do a little ramp. You stop. You do full tomography, which I'm sure you guys know what it is. You just do you do e-rotation to measure x and y before, or you just do direct z measurement, and you get one single point in here. And you continue it, and you get this skipped path, essentially, on the Bloch sphere that tells you the state of the qubit. So adiabatically, you know that if you do it very slowly, it would have been over the meridian, but now it's deviate of it, and this deflection is telling you about the local curvature. If you do the math according to Polkovnikov relation, you just need to integrate over this deflection to tell you about the churn number, and that's the churn number we get out of it. It's pretty amazing that you do a measurement which there is nothing about it to be saying to be discrete, but at the end of the day, you get something very close to 1 after you've done all the calibration, of course, properly. Okay, so why the number is 1? Again, back to the Gauss's law analogy I mentioned. Because because there is a degeneracy in this Hamiltonian, which is located at the origin. If all these parameters are 0, then this is a degeneracy point, and then the manifold we constructed is enclosing that degeneracy, and that's why the churn number is the curvature is sensing it, that the churn number is reflected in the churn number. Yes?
I was wondering, I thought the churn number is independent actually of connection by which you compute it.
It depends if you have included a singularity, but the shape of it is independent. So at the end of the talk, I show you the independence of the shape. So let's move to a condensed matter model, which we want to make a topological phase transition for it. And this model hopefully is familiar to all of you guys. It's called the Haldane model. And Haldane in 1988 was trying to find a model which you can get these plateaus and these topological phase transition without having a large magnetic field, with just breaking the symmetry locally by coming with a very strange looking magnetic field for each unit cell of graphene, and keep in mind even graphene, the word graphene, only the word graphene existed at that time, and they called it 2D graphite. So anyways, the Hamiltonian of the system has been figured out. During the high symmetry point of the Brillouin zone, it takes this form. And then he said that the topological phase transition happens when you have this ratio of for the mass terms. So that's all you need to keep in mind. But then we look at the qubit system, and this is the parameter space, and you can see that the Hamiltonian can be rewritten, not that difficult if you just reparameterize it. It's very much looking like this one. And this is the mapping that you need to know to go from one system to another. So this model can be fully understood with a single qubit because this ratio of these two parameters, H0 and H are playing the same role as these two parameters which sets up the phase transition for you. Just to be very clear, because many people got this confused, it's an important point that now we have single qubit which explore the entire Brillouin zone for you. So I picked up this picture and I'm trying it on you guys to see how you react. But there are so many electrons on the Brillouin zone, like these wheat field, but then there is a single qubit which is feeling it. So in single qubit you can explore a non-interacting Brillouin zone, no matter how shaped it is. It's just like many electrons, if they're not interacting, because it maps to the parameter space of it, can be explored with a single qubit. So it's not the phase space of a single qubit. There is no phase space, but the parameters of it is really represent the texture of the Brillouin zone for you. You can explore that for you. So let's move this manifold up and down and see if we can construct this phase diagram that we see over there. So, this axis is HR, which is the radius of the manifold, and this axis is H0, which is the position of the center of the manifold, and then each point essentially represents the manifold, the full measurement of the Chern number, and then the intensity is the measured Chern number. And you can see that clearly we see two distinct values. And as the ratio of H0 over HR changed from 1, you jump from one to another, which is not that surprising. As I mentioned, this is depend on the singularity and if you enclose it or not. The singularity of the system is at origin, and as soon as you miss it, the Chern number drops to 0. So this is fully understandable. We kind of benchmark using this to benchmark our understanding of the system. We can do the texture of it. Yeah, I say it briefly. So let's forget about the method of Polkovnikov for a second. This is fully adiabatic state preparation. It's just for this simple system, we can do this to really see how the states look like. So you ramp the parameter to each point in the parameter space, and then there's a mapping from the parameter space to momentum space, and each vector is what we measure for each point. And so you can see, make the full spin texture of the state on the block sphere, and you can see how it goes over the transition, and then you can see really the action happens along these lines, so you can make a cut and continuously change this parameter and see how the state changes as you go through the transition. And this is a direct adiabatic method, and you can compare it with the result from a dynamical method, and you can see good agreement. But of course, this method requires this differentiation, which becomes very costly, and preparation of this state for 2 qubits is also very difficult. So this really cannot be pushed more than that, but the dynamical method has no problem. So if you want to look at the 2 qubit system, we need to go beyond this idea of having a fixed coupling. So we need to really make this tunable, and then we really have the full control over the Hamiltonian. And that was the first challenge we need to address. And in fact, making tunable coupler is goes many, many years old, and flux qubit seems a very ideal paradigm for this case. And there are many works, in fact, some done at UCSB to try to do it. But also flux qubits always have some noise issues, and it's not the best qubit. So maybe the real challenge is, can you make it while you're maintaining the coherence of the system without damaging the coherence? Well, yeah, we can connect it. I don't have the coherence data, but you can take my words that it really stayed coherent. So the 2 qubits are capacitively coupled, so it's easy to fix that by just moving them away or something. But there is no coupling, there is no flux from here to here, there is no loop, there's both open loop. But if you start thinking that you need only an AC excitation is from here to here, you can start adding some small elements, linear elements, which damage your nonlinearity a little bit, but you can engineer that. and then you can add adjustable inductance in between them. And by adjusting the flux into this loop, you can connect the two loops, and now you can see they're essentially inductively coupled to each other. So you can really work out the math rather easily if you think of LC circuits. There are two LC oscillators coupled, and then you can see how, what's the mutual M. You put an excitation here, how much it gets to that side, and you work it, and you get a really nice relation, which is almost cosine shape. Note that this is denominator of the denominator, so it's pretty decent sinusoidal relation. So you can really, by changing the flux into this loop, you can really control the G. As you can see in this work that we did, the spectroscopy of the system, this knob is essentially this delta, changing the flux into this loop, and you can see there are two frequencies of the system, and without detuning them, they really can be, the coupling could be off. So the two qubits are right on resonance, but they don't see each other. That's essentially pretty good off. As we do any swap or anything, there's absolutely nothing gets from one side to another. Well, there were calibration challenges and such, but that's aside. It is really key now for quantum simulation. And this is for you if you're a Hamiltonian lover, yeah, just subject to constraint, and if you can solve it. But my point is that this is the way to gain intuition into this problem, and this is really doesn't take you that far. So this is the system that we put together, and after fabbing. And you can see the place of these 7 knobs that we need to control this Hamiltonian. These are the driver lines in here, and then this G knob, which controls this G coupling in here, and then the added inductances and the flux into the qubit. So that's what it takes to do two fully controlled coupled qubits. So now we're going to do a little more complicated phase diagrams, which is a little hard to imagine. It's now multi-dimensional beyond that 3-dimensional phase, but you can still imagine the phase diagram the manifold I'm trying to constrain in the limit that this G is 0. I'm going to put a manifold in one qubit, Q2, which is centered around origin, but I'm going to put another manifold in here which goes up and down. And this picture fails when there is non-zero G, but in the limit you can see what sort of manifolds we have in mind to construct. So we just rewrite this Hamiltonian trivially. And this is the phase diagram of the system as a function of these parameters J, HR, and then H naught. So let's see if we can digest these 3 cuts that I made through. These are the experimental data, and this is the analytical result of the case. So we can start from here when G is 0. This is kind of it can be understood easily because in this panel G is 0. So there are 2 independent qubits, and one of them is sitting at the manifold is at the origin, another one the manifold moves up and down. So one of them is always have channel 1, another one have churn going from 1 to 0, and then you add up the 2, so you go from 1 to 2 to 1. So that's all into this one. But as you start the coupling between them, you see an emergence of the field that has a churn number of 0, and it comes on with the interaction. It appears when the G is strong, it appears, and then pushes this phase away. And then, you may say, oh, it's a numerical mistake or something, so this panel, and then you make a cut perpendicular to that. And you see, yes, indeed, it comes even when you make cuts into the phase space in the other direction. When G is becoming strong and dominating and going beyond HR, you start to see this phase. So let's go and see how we can make sense of these phases a little more carefully. So let's take this limit that G and H naught are small and HR is dominating. Again, there is no coupling. We have 2 separate qubits. There is an external field. They do follow it, and it's like a paramagnetic. You put the spins. There is external field. They follow it. 1 plus 1 gives you the churn number of 2. In the other limit, when there is a strongly coupled, they're not really listening much with the external drive. They just they are in a singlet state, and then it pretty much look an anti-ferromagnetic. They're not going to cover any singularity of the system. But keep in mind, these are very hand-wavy arguments. You really need to look at the singularities of the Hamiltonian, figure out where the singularities of this Hamiltonian is, and where they are as you change the parameters. So let me make a cut in ABC along this line. There are two singularities of the Hamiltonian. Is enclosed by manifold at point A, and at this dashed line B, one of them escapes the manifold, and that's why the Chern number jumps from 2 to 1. Along this line, there are two singularities enclosed, and then G pushes both them out simultaneously, and the Chern number suddenly jumps from 2 to 0. Yeah, just to be very clear on this, it is anti-ferromagnetic parameter. It's just a hand wavy of talking. As you go from a ramp, let's consider this point, and I figure out I writing the eigenstates of the problem for each point during the ramp, the adiabatic limit. This is crazy looking, but the beauty of the dynamic method is, regardless of this complication, it just gives you the exact number at the end. The deviation kind of senses the local curvature and just gives you the number at the end of the day. So let me summarize. We picked up a method suggested by Polkovnikov, and it's really generalizable to measure the topological properties of manifolds. And then we benchmark it by doing something which we have some intuition and some feeling is rather simple, the Haldane model, non-interacting limit, and then we construct a phase diagram for that. And then we could even do adiabatic measurement to construct the spin texture of the first Brillouin zone. But then we show the power of the method and the power of superconducting qubits to fully control a two interacting spin Hamiltonian and constructed the phase diagram for that. And this is what we have in the fridge now, or soon you're going to have in the fridge. We had one try of it. This is 3 coupled qubits. And we're going to do SCS and among other experiments with it. Yeah, thank you.
Any questions for Ted? Mike?
So you have to pull out the term that's linear in V.
Yes, if you
There's high order terms you have to sort of experimentally
actually
find.
let me heal to so this kind of answers your question. And so here, if you could see, we are changing the shape of the manifold and also the speed of going over it. So this is the Chern number of the system. This is single spin 1/2. The Chern number is 1. So the whole curve meant to be red. But if you do the ramp very fast, the time it takes to go from up to down is very fast. You're not going to get it. The number is wrong. But if you start doing it slowly, you start to get the number. So that answers your question, that if the ramps are fast, the reading is wrong, because the term in the order of V squared would be substantial. You cannot ignore that, and it's independent of it.
But if you're trying to use this as a tool, I mean, are you just using the answer though to? I mean,
yeah, no, there are challenges in a sense that, okay, how slow do we need to go, and this is depend on the level separation, and the level separation gets small, then you have to, right? You were trying to avoid going to higher level. Yeah, that's the challenge for this for the method.
Any other questions? Thank you.